Welcome to all my learning students. Today I will discuss electronic spectra. This is very important topic for net get set student. It is also very important topics for M.Sc student. In this topic I will discuss electronic spectra of transition metal only. The electronic spectra involves promotion of the electrons from one energy level to a higher energy levels. Such transitions of electrons are called electronic transitions. The electronic transitions are of higher energy and always accompanied by lower vibrational and rotational transition. The selection rule. What is selection rule? Selection rules is guided for electronic transitions. There are two electronic transitions selection rule. One is spin multiplicity rule. What is spin multiplicity rule? The transitions in which the number of unpaired electrons changes in going from a lower to a higher energy state are referred to as a spin or multiplicity is forbidden. This suggests that the transitions to only those excited states are to transitions to only those excited states are to be considered which have the same spin of multiplicity as the ground state. Another selection rule, that is Lapode forbidden rule. Those rules states that the transitions which do not involve a change in the subsidiary quantum number, that is delta L is equal to 0, are Lapode forbidden if the molecule has center of the symmetry. This is very important rule. Here we draw out a table of various transition metal system and various example which is Laplace transition is allowed or forbidden and spin multiplicity is allowed and forbidden. If you see D7 system, say example cobalt Br4 2 minus, this is if see the CFT electronic configuration, that is T2G5 Eg2, that is Laplace transition is allowed. In this, why it is actually tetrahedral complexes, and that is why Laplace transition is allowed and spin multiplicity also allow. In this case, the ground state electronic term symbol, that is 4F and 4P also. If you D5 systems and say MnBr4 2 minus, also this is tetrahedral or square planar complexes. Here center of symmetry is absent and Laplace transition is allowed and spin multiplicity in this case is forbidden because of D5 systems. And another example MnH2O6 2 plus, that is octahedral complexes. It is also D5 system, and being octahedral complexes, here center of symmetry is present, and that is why Laplace transition is forbidden and spin multiplicity also forbidden. If you see D2 systems, say example vanadium H2O whole 6 3 plus, and that is D2 systems, the electronic configuration will be T2G2 Eg0. In this case, the Laplace is forbidden for octahedral complexes and spin multiplicity is allowed, and same for the 3 systems, that is CrH2O whole 6 3 plus, and same for result as D2 system. If we see D8 systems, say example NH3 whole 6 2 plus, that is also octahedral complexes. The CFT electronic configuration in this case will be T2G6 Eg2, as NH3 is strong field ligands, and that is octahedral complexes, and that is why the Laporte transition is not allowed, that is forbidden, and spin multiplicity is allowed. If you consider D7 systems, cobalt H2 whole 6 2 plus, this is also octahedral complexes, and electronic configuration will be T to D6 is 2, and also the Laporte transition is forbidden and spin multiplicity allowed. And this is very example, so many example are point out here, but the proper explanation of CFT electronic configuration, which is Laporte transitions or forbidden and spin multiplicity allow or forbidden, it is very well defined explained. When we study CFT in the CFT chapter, you let's see why this is those example is point out here. Is Laporte forbidden or not, or spin multiplicity rule is allowed or not? In this chapter CFT we can see in electronic transitions, the splitting of a Russell-Saunders state in octahedral and tetrahedral crystal field. It is very important topics in this chapter. In order to understand the nature of the electronic transitions in transitions metal complexes, let us study the splitting of electron energy levels and spectroscopic terms into various components. Various point is mentioned here. Point 1. An s orbital is spherically symmetrical, and hence this is not affected by an octahedral or any other field. Similar is the case with spectroscopic terms S. Point 2. These p orbital are directional and affected by an octahedral field. However, since a set of p orbitals are all affected equally and their energy levels remains equal and no splittings occurs, and similar in this case of spectroscopic terms p. That is point 1 and point 2 say that the S in case of s orbital, this being symmetrical, it is not affected in crystal field in presence of crystal field, and that is why the term symbol is capital S. And same for p orbital is being 3p orbital is symmetrical, and same types of affectations by crystal field stabilization energy or crystal field, and that is why the similar spectroscopic term is defined as capital P. Point 3. If you see the picture of d orbitals, you can see it is different from s and p orbitals. So let's see, a set of 5 d orbitals is split by an equal octahedral field into two levels, that is T2G sets and EG sets. In case of T2G sets, the orbitals go dxy, dyz and dzx, and in case of EG sets, the orbitals goes dx square minus y square and dz square. The difference in the energy between two sets is written as 10 dq. The T2G levels is steeply degenerate and EG sets is doubly degenerate in presence of crystal field. And for D1 electronic configurations, the ground state is 2dd, that is L equal to 2, 2s plus 1, this is spin multiplicity is equal to 2, and in T2G, that is dxy, dyz and dzx, and EG dx square minus y square and dz square electronic energy levels corresponds with the T2G and EG spectroscopic terms, and thus the spectroscopic term D compromised deeply degenerate T and doubly degenerate E compounds. In case of F orbital, the 7f orbital is also splitted in presence of external crystal field. Let's say a set of 7 f orbital is splitted by an octahedral field into 3 levels. For F1 electronic configuration, the ground state is 3f state which gets splitted into steeply degenerate as T1G state, a triply degenerate T2G levels, and a single A2G state. And thus, the spectroscopic term of F comprises of two triply degenerate T1 and T2 and a single degenerate A1 compounds. Thus, we can say that is, in octahedral field, the S and P state are not splitted. These states are splitted into two states. F state are splitted into three states, and G state are splitted into four states. And those states splitted by external field are called Mulliken symbols. If you see some Mulliken term symbol, then you can get we headline splitting of term free ions or atoms into Mulliken symbol in an octahedral or tetrahedral complexes. That is, we draw out a table. One side terms S, P, D, F, G and Mulliken term symbols represents as in case of S, A1, in case of P, T1, in case of D, E plus T2, in case of F, A2 plus T1 plus T2, in case of G, A1 plus E plus T1 plus T2, in case of H, we can write E plus T1 plus T1 plus T2, in case of I, we can get A1 plus A2 plus E plus T1 plus T2 plus T2. And those term symbol are is come from group theory. This is very important in case of Mulliken term symbol. And in this chapter for electronic transitions, various net exam these types of questions are come out. And in case you can remember this term symbol, because in a short times you cannot draw out or calculate this term symbol, and that is why you must remember this term symbol in case of F, in case of P, in case of D, in case of F, in case of H. This Mulliken term symbol will be must remember out, because in the net question in the short times you can answer if you remember this. If we focus the Mulliken symbols in octahedral complexes, in case of octahedral complexes, we also draw out a table. One side spectroscopic term symbols and other side Mulliken symbol in octahedral field. In case of S, that is Mulliken symbol is A1. In case of P, that is T1G. G means in case of octahedral complexes. And D, in case of D, the term symbol is EG plus T2G. In case of F, the term symbol is A2G plus T1G plus T2G. In case of G, the term symbol is A1G plus EG plus T1G plus T2G. In case of H, the term symbol is EG plus T1G plus T1G plus T2G. In case of I, the term symbol is A1G plus A2G plus EG plus T1G plus T2G plus T2G. And those term symbol in case of octahedral complexes, this is very important for net exam and GATE exams, also chemistry based all India exams. And this in this case, in to answer in short times, you must remember this term symbol in the minds. Here we point out the spectra of D1 and D9 octahedral complexes. We let's see the energy versus crystal field state plotted in case of D1 system from CFT concept, that is split into two sets, that is T2G set and EG sets. In case of T2G set, the energy value is minus 0.4 del 0, and in case of EG sets, there is energy value is 0.6 del 0, which is known from CFT configurations, crystal field energy configurations or theory, crystal field from crystal field theory. We point out an example, titanium H2O whole 6 3 plus, that is D1 system, and that is why in this case titanium 3 plus complexes, the splitted will be same types, and in case of D9 systems, the also same types electronic configuration will be happened? Because D9 is whole mirror image of D1 systems. In case of D9, this is actually whole mirror image of D1 systems, and that is why in two cases the molecular term symbol will be same. If you see D1 and D9 octahedral complexes, that is, the term symbol is 2D. The ground state term symbol of D1 and D9 systems in octahedral complexes 2D, and in case of 2D, it is split in doubly, and hence it has two state, that is T2G state and EG state. In case of D1 system, that is down T2G set and up EG set. In case of D9 systems, EG set is down and T2G set is up. That is, in case of D1 and D9, that is inverse, whole inverse. The term symbol will be, in case of D1 and D9, is same in case of molecular term symbol, but it is will be in inverse. This is very important topic to answer net exam question paper in spectroscopy term symbol. It is very point out this for focusing. If you see study D1 systems, you can also study D9 systems. If you study D9 systems, you can also have to study D1 systems, because it is whole inverse. Clear? And this energy value also is point out here, and but the total focus you must in case the features. If you see D2 and D8 octahedral complexes, in case of D2 and D8 systems, the term symbol will be 3F. The ground state term symbol is 3F, and that is F is split into 3 state, Tibli state, that is T1G state, T2G state, and A2G state. In case of D2 systems in octahedral complexes, it is split 3 state, in top AG, A2G, and middle T2G, and bottom T1G. This is 3 state. If we write, in case of F, we write down in bracket F. But if we consider F system, 3P systems, and also we dotted line it is down in case of D2 system, that is 3T1G P in case of bracket P. That is because of if we see or write term symbol, in case of D2 and D8 systems, many term symbol is possible, but we study the ground state term symbol. That is, it means it is not the only 3F term symbol, but there are many term symbol. Then we see in case of F, that is these types of splitted. In case of P, there is one types of splitted, only P, that is one term symbol P. In case of P orbital, this one not splitted. In case of external magnetic field, that is we write it 3T1GP. But in case of D8 octahedral complexes, if you see the whole universe of D2 systems, that is where in case of D2 system, the top A2GF. In case of D8 systems, that is bottom A2GF. In case of that is middle T2GF. That is in case of also middle T2GF. But it is energetically whole universe. That is where energy is, in case of D2 energy will be much, in case of D8 system energy is less. And in T2G, where in case of D2 is bottom, but in case of D8 is top, that is 3T1G. In case of F, in case of in bracket. But if in case of similarly, where the P system term symbol is 3P, that is P system term symbol. In case of D2 energy is less, but in case of D8 system the energy is much, and that is why at top point 3T1G, which is come for P system, P orbital, that is P orbital. And this is very important diagram for D2 and D8 systems. For net exam, it is also remember in this mind, because in basis on this diagram you can Answer: various transition, spectroscopic transition, which is must 8 mark in every net exam. If you see those two diagram in mind, if man must mark 8 or 6 or 8 mark. In this case, it is very important topic for net exam. In case of D7 and D3 systems in octahedral complexes, same. There the ground state term symbol is 4F and F is split into 3 state. That is, if we consider D3 systems in octahedral complexes, the diagram of that is bottom A2G and then next T2G and top T1G, that is bracket F. And in case of p orbital, that is T1G p and at top. In case of D3 system, for remember, if you see D8 systems in before page, that is same electronic configuration, that is spectroscopic term symbol, but here is ground state is 4F, but other in this before page the term symbol is 3F, and this is multiplicity 3, and in this case 4, and that is, but in D8 and D3 system, but symmetrical pattern. This is for remember, you can easy for remember. But in case of D7 systems, you see the whole universe of D3 systems, that is where bottom A2G and in this case of top A2G, and in this middle, that is T2G, and in case of top D3, and but in case of D7, in case of D7, that is bottom T1G, that is bracket F, and same for P system, that is where in case of D3 the p orbital the energy is higher, but in case of the p orbital the energy level is less, and that is it exists as T1GP, that is between it exists between T2GF and A2GF. In this energy barrier, in this middle point, it is exist. It is very important topic for D7 and D3 systems in case of octahedral complexes. In case of D4 and D6 octahedral complexes, and there is term symbol is 5D, but actually the d orbitals term symbol d is split into two state, double state, that is T2G and EG, and that is one in case of D4 systems, that is split as EG and T2G, that is we bottom EG sets and top T2G sets, and in case of D6 system whole universe, that is bottom to top, top to bottom. In case it is actually similar D2 D8 system. This is actually same case of happen in case of D1 D9 systems. D1 D9 system, where the term spin multiplicity is 2, and but here the spin multiplicity is 5. Same for D1 D9 system and D4 D6 system. That is for remember this we also sort the all diagrams in draw out similar pattern, successive pattern, then similar D4 and D6 systems, and D1 D9 systems, D3 D8 system, and also D2 D8 system, and D3 D7 system are similar. Now, if we consider tetrahedral complexes, that is tetrahedral field, that is in case of D1 D9 systems, how types is splitted. In actually tetrahedral field or octahedral field is nothing but actually it is split in terms of term symbol, on basis of term symbol. That is in D1 D9 systems, the term symbol is 2D, and hence this case this is split into E and T2. Actually G is not written here because G is written only in this case of G system, that is where the center of symmetry, that octahedral complexes is present, but in tetrahedral case the center of symmetry is not present, and that is why we write in only T2 and E. And in D, you consider D1, that is tetrahedral field, E set is down and top T2, and in case of D9 whole universe, that is top to bottom, bottom to top. Actually this is actually in case of octahedral complexes, tetrahedral complexes. In case of octahedral complexes, in case of tetrahedral complexes, this is whole universe. In case of octahedral complexes, that is EG 2G in case of D1 systems. In case of octahedral complexes, in what D1 systems, that is EG set in top and T2 set is down, but in case of D1 system tetrahedral is inverse, and D9 system same and vice versa. In case of D2 and D8 systems in tetrahedral complexes, in case of D2 tetrahedral complexes, the ground state term symbol is 3f and f orbital is split into 3. In case of D2, the top point A2f, next T2f, and then energetically higher, that is T1f. But if you consider p orbital, that is T1 p. But in case of D8 system in tetrahedral complexes, that is whole universe, that is 3T1 top to bottom here, and then 3T2f, and that in and then at this top 3A2. Actually, in case of p orbital 3f, and in this here in this case D8 system, that is 3p1, that is between of T2 and A2 systems. Energy is middle point. That is actually whole inverse of D8 and D2 systems. That is actually D2. If you see D2 systems in case of tetrahedral, that is in inverse of D2 octahedral complexes, and D8 systems is also opposite of octahedral complexes and vice versa. See D4 and D6 tetrahedral complexes, the term symbol is 5D, and being D, it is split into two states, that is E and T2. In case of D4 tetrahedral complexes, T2 is lowest energy, and that is bottom point exist, and higher energy E set in top exist. And in case of D6 system tetrahedral complexes, that is vice versa, at the tetrahedral bottom point in case of D4 will be go D6, in case of D6 top point 5T2, and E higher energy E set in case of D4 will be go in case of D6 bottom point, that is lowest energy. And this presentation, the energy presentation diagram for Mulliken term symbol this. In case of D3 and D7 tetrahedral complexes, that is ground state 4f term symbol, it is split into three states. That is in case of D3 system tetrahedral, that is 4T1, 4T2 and 4A2. This is F, F, F. And in case of D7, this is whole reverse, that is A2, T2 and T1, that is top to bottom and bottom to top. And in case of p orbital, that is same. In case of D7 system, the energy of p orbital is 4f1, that is higher. And in case of D3 system, this is energy level middle point of 4T2f and 4A2f, that is energy level middle point 4T1p. And it's very interesting term symbol presentation of D3 and D7 tetrahedral complexes. If you see the combined form of octahedral and tetrahedral complexes, and the next page we draw out this. If we see D2, D3, D7, D8 octahedral and tetrahedral complexes in a together, then we can write the term symbol, ground state term symbol is F, that is spin multiplicity is not written because D8 and D3 systems, D3, D7 or D8 systems spin multiplicity is different, but term symbol is F. And this F orbital in case of tetrahedral and octahedral complexes, those types are splitted. If you see D2, D7 octahedral complexes, and in case of D3 and D8 tetrahedral complexes, the same electronic configuration or Mulliken's configurations. And D3, D8 octahedral complexes and D2, D7 tetrahedral complexes, same Mulliken's presentations. And that is in combined form we can write so that we can mind it in for net exam preparations. It is short form, we can combine these diagrams. If we remember this diagram and whole D3, D8 octahedral complexation, D2 D7 tetrahedral complexation, D2 D7 octahedral complexation, D3 D8 tetrahedral complexations in a form we can get out these types of presentations. Okay. Another, if we combine D2 and D8 octahedral and tetrahedral complexes, then we can get the presentations D2 and D8, D2 tetrahedral and D8 octahedral complexes same term symbol, and D2 and D8, D2 octahedral and D8 tetrahedral complexes same electronic configuration or Mulliken's configurations. But in case of we see that G and F, actually G is not should written here. Actually we can should written. Actually in case of if you consider octahedral complexes, that you can see in D2 system permutation T1G and T2G, T1G, A2G, F, etc. And if we consider D8 tetrahedral complexation, the same, but G is not written. That is, we written T1, T2, T1, A2A, these types. And same for D8 systems and D2 tetrahedral complexes. And that is inverse of D2 octahedral and D8 tetrahedral complexes. That is same, and but reverse. Over there, top and bottom and top and vice versa. And clear, it is combined form of D2 and D8 octahedral and tetrahedral complexes. Here we draw out in questions of NET exam. Here 3 transitions are expected. That is 1, 3 T1GF, 2, 3 T2GF. Point 2, 3 T1GF, 2, 3 A2GF. Point 3, 3 T1GF, 2, 3 T1G. In this case of their spin multiplicity in same, and those 3 transition is allowed according to spin selection rule. The question is, which transition is allowed and wavelength is maximum? That is, wavelength is maximum, that means energy is minimum. Which transition is allowed and maximum wavelength, that is what is minimum energy. That is, in this, if you see the question, that is in case of F and P, this combined form F and P orbitals. That is, 2 orbital is combined here. Actually, F term symbol is come from D orbitals and P is from P. Actually, P and D combined transitions. This in this case. And question, this is question and answer is next page. If you see the diagram of 3F, that is the spin multiplicity F 3 and term symbol is F, and we see the whole transition of 3F. One side, that is the T1GF, T2GF, then 3 T1GP and 3 A2GF. In case of this, actually in case of this transition is known, and if you see the energy diagram along with x-axis, this is energy is lowest is 3 T1GF, and then the energy 3 T2GF, and then next energy, that is P entered, P orbital is entered, that is 3 T1GP, and higher the energy is 3 A2GF. That is, in case of middle point 3 2GF and 3 T2GF, this enter the energy level, middle point energy level, that is 3 T1GP. And this from the diagram, third transitions. This third transition is energies, that is transition 3 is energies much, and that is wavelength is less. This mass energy means the wavelength is less. And first transition, that is T1G to T2GF, T1GF to T2GF. This transition is energy is less, and that is why wavelength is maximum. And the answer is 0.3. That is, answer will be 3 T1GF to 3 T2G. 3 T2G. Clear? This is actually answer. And if you in this question, we the question want the maximum wavelength, but other question, the why, which is maximum energy, minimum energy or minimum wavelength, that is you can answer whole answer from this diagram. Okay. Special thanks to you for give your valuable time and listens my topic.